Real exam questions. This is question 36. It's about slab design and the method of equal deflection. Prove the load transfer formula for the equal deflection method for a rectangular isotropic slab in the general case. What will this formula be if the slab is not isotropic? That means that the stiffness in the direction of A is different from the stiffness in direction B. Apply this to a slab type 3. Slab type 3 is when two opposite sides are fixed ends and two other opposite sides are simply supported. Apply this to a slab type 3 and determine the percentage of load transfer in the direction of A and B, knowing that the slab is loaded with a uniformly distributed load of Q kilonewton per square meter. The total load is the load in direction A plus the load in direction B, or the load in direction B is equal to the total load minus the total load in direction A. Isotropic means that the stiffness in direction A is equal to the stiffness in direction B. Now we are looking at the deflection in midspan, which is given by a general formula, and omega A, it depends on the conditions at the support. Same applies for omega B. Now we use the method of equal deflection. It means that WA must be equal to WB, or by using those two formulas, we can rewrite this as follows. Now we will substitute the value of the load in the direction of B. So QB is Q minus QA. We are rearranging it for QA, and we arrive at the equation QA over Q is equal to this formula, or you can write it more easily like this. Now we will apply it to an anisotropic plate, slab, where the stiffness is different in both directions. So we will use again the general formula, which is the W or the deflection in direction A must be equal to WB, the deflection in direction B. We know that we have now this relationship if we're substituting the value of WA and WB, but this time we cannot say that AE stiffness in A is equal to the stiffness in B, and so it stays in the formulation. The only thing we can assume, of course, is that the modulus of elasticity in direction A is equal to the modulus of elasticity of the concrete in direction B. In a case that the, for instance, the slab is cracked in direction A and not in direction B, then of course you cannot write this, and then you have to take into account the whole value. Simplifying the equation, then we are regrouping again for QA. You see that now there's an additional term in the equation depending on the stiffness of the slab. And rearranging it, we arrive at this formula. So you see, instead of omega A divided by omega B, we have now the EP divided by EA. We will now apply this formula to a case of slab type 3, where the stiffness in direction of B is 2 and in direction of A is 1. So this is the general formula. Omega A is of course, this is the direction of A, so it's clamped, or it's fixed support, so that means omega A is 1. And in the other direction, it's simply supported, so omega B is 5. The length in direction B is 5 and in A 7.5. So we assume it's just a scale factor, that the stiffness in direction A is 1 and the stiffness in direction B is then 2. So we use this formula, plug in the different variables and calculate it. So we arrive at QA over Q is equal to 0.33. So 1/3 of the total load is coming from direction A, and 2/3 of the load is in direction B.